So, good morning, everybody. This is Beatrice Plaza speaking from the University of the Basque Country, the Faculty of Economics and Business. We are within the European project entitled Education for Technological Literacy and Inclusion, and we are delivering the seminars for lectures in the field of data science. Okay, with the very basics, our target are the culture managers, managers of cultural tourist destinations within the field of culture management and cultural economics. Okay, we are trying to be very practical, and we are obviously the presentations, they are reliable but very practical, trying to get through and make an understanding of the topics. For those who are not so used, let's say, or less used, let's say, to this type of analysis. Okay. So today we will get into regression analysis with cross-sectional data. Can you see the PowerPoint? Can you see the PowerPoint? Yes, lovely, thank you. And for this, we will use Google Analytics data, okay? Google Analytics measures I will use the presentation delivered on Monday, excuse me, and then move on to the calculations, explanation, calculations, regression analysis with cross-sectional data. Okay. So as we already saw on Monday, we are measuring the website traffic quality through Google Analytics. Okay. Is this important? The website we're analyzing is this one, and we will be employing two methods. One, plain cross-sectional data today, and tomorrow regression with time series analysis. Okay, so let's start with the plain cross-sectional data. Okay, this is the data. Okay? We have different variables extracted from the web analytics system. First, we have extracted, this is primary data. This means that everything has been extracted directly from the Google Analytics system, okay? So the first column is the number of visits by traffic sources. We build up Excel table with different variables. We have first traffic sources, direct traffic. Direct traffic means that they enter the website by writing the domain directly. Reference sites, these are links, search engines like Google, for instance. Then we employ the top 10 reference sites, Wikipedia in English, Wikipedia in Netherlands. We took the top ones, okay? In Spanish, the fourth one is the University of Basque Country, Wikipedia in Deutsch, in German, University of Valencia, and some more platforms over there. Then we made the distinction between Google and Yahoo, and then at the end we chose the 15 keywords by traffic, okay? All keywords together, and then there is a selection of keywords: Bilbao, urban, regeneration, Guggenheim Scholar, museum, cultural city, brand, effect, plaza, image, European tourism, and design. These are the best. This is a set of keywords that are powering the positioning of this website. Okay. Because we are talking about the internet, and we are talking about the positioning of this website on the internet through the traffic sources. This is the research question here. Any question? No. So I'll show you. Now we will go to the system to to see where the data comes from. Okay, so I'm going to log in Google Analytics. Google Analytics. Here we are. And within Google Analytics, I need a Google, at least in our case, we set up the account with a Google account. Okay. So this is
Beatriz, you said that this Google Analytics from, I don't know, one date in July will stop according to the European rules.
no, they will not stop, they will change.
Oh, they will change. So I can
Yes.
go with my Gmail account and do.
Yes, you can set up an account.
Okay.
You will need to, there are 8 days left, 9 days left. Can you see it?
Yes, yes.
Yes, 9 days left. Google is going to aggregate data and make data more anonymous, okay?
Yes, I understood that.
It is anonymous somehow, but not enough for the European legislation
Okay.
rules.
Okay.
And so they are going to update the system, the Google Analytics system, to the European Union rules, privacy rules.
Okay. But here in
Yes.
this Google Analytics, I can find also information about Portuguese cultural organizations. You think so?
You need to activate your website to the Google Analytics.
Okay.
Here the website, I'll say no thanks. Here the website we are tracking is this one.
Okay.
Can you see the pointer?
Yes, yes, yes.
Yes, it's colasonbilbao.info. This is the website we are tracking. Okay. Obviously, we want to monitor who is accessing the website, and we are interested in some very specific markets, okay, countries, and this is why we monitor it. Okay.
Okay. So I have to find if there's a link in Portugal for that too.
Yes, you need to. Yes, you need to activate the website. So can you see that I'm customizing the
Yeah.
dates?
Yeah.
So I'm asking from January 2007 to
The end of month of
the end of
May.
Okay.
Mm-hmm.
Okay. Okay. And we have the data here. This is the number of this is the number of new users that access the website.
Mm-hmm.
Okay. This makes sense because last year was the 25th anniversary of the Guggenheim Bilbao. So you can see that there was an increase in interest in the topic here. The number of users on the right-hand side increased. People that were looking for this topic in the website. Okay, this is time series. This is time series. You have one variable from the year 2007, and you have a continuous time series up to now. This is time series. Okay, so and we can perform regression with time series. It will do it tomorrow by downloading time series and perform a regression there. Okay. We can perform analysis with cross-sectional data. This is cross-sectional data, okay? Because at a specific point of time, you have the value of it. Can you see it? We have bounce rate here. We have number of pages per session. average session duration, okay? So it is very easy. The only thing we did is we took the values here and we build up the Excel, okay? As easy as this, okay? Excuse me, can I ask you, do you see the table here?
Yeah, but if you can put a little bit bigger the zoom, it's better.
Okay,
Thank you.
you're welcome. Okay, so this is by countries, but the traffic sources as a whole, it will be the same, okay? So bounce rate, and then you have for direct visits, for instance, bounce rate, and you copy paste it, okay? Number of pages per session and average session duration here, okay? We calculate return rate. The system doesn't supply return rate, but it is easy because return rate is total users minus the new users. So we calculate it's easy to calculate the return rate, okay? So, and this is how the system itself doesn't supply any inference analysis, no regression analysis, but it supplies very valuable data. That if it is extracted properly and if it is applied properly in the regression, we can obtain results. Okay. And here I have a breakdown of the new users by countries. And you can see that most of the visitors most of the traffic comes from the USA, United States, and then the second country is the UK, United Kingdom, Great Britain here, and the third one is Spain. Considering that the website is located in Spain, we think it is good news to see the traffic the website is generating in these countries. This means that they access the website and okay. Okay, any question in connection with this? So this is where the data comes from, okay? The data mining. There is a whole working here by extracting data mining. So I would like to underline again, this would be cross-sectional data. And you have data at a specific point of time, okay? So we have bounce rate, we have pages per visit, we have the average session duration, and this would be time series, okay? This is time series. You have the data here from the year this is monthly data, okay? From January 2017 up to May 2023, time series. Okay, so I'm going to get out of the website, okay? Get out of the web analytics system and go.
Lost.
Yeah.
Patrick.
Let me see if she returns. I can send her a WhatsApp probably. Did you lose internet She's rebooting.
Good morning, everybody again. I'm sorry. My PC had a problem, but I'm back again. Okay, so we showed the data extraction in Google Analytics. Wait a minute. Yes, we are recording. And then now we go to the PowerPoint. Okay. Can you see the PowerPoint? So this table, and can you see the PowerPoint?
Yes, yes.
Yes, this table, I showed you where the data comes from, okay? It is primary data, and it has been extracted, collected, in this case, manually, okay? It can also be extracted automatically by coding with Python, okay? But in this case, we did it manually, okay? Okay, so we have these graphs, as we saw on Monday. The bigger the return visit rate, the bigger the number of pages per visit. It makes sense because visitors that come back to the website show interest in the website. So it is okay. This excuse me. So we are here, the bigger the return visit rate, the bigger the number of pages per visit. Okay, it makes sense because people who return to the website, I'm sorry that I'm repeating, they stay more, they stay longer. The relationship between bounce rate and return rate, the higher the bounce rate, the lower the return visit. And this also makes sense. Bounce means that they come and they leave immediately. So we are interested in traffic source with very low bounce rate, okay? Very low bounce rate. The lower the bounce rate, the better. The lower the bounce rate, the better quality of the data. The lower the bounce rate, the better quality of the traffic. The lower the bounce rate, the bigger the return rate, the bigger the amount of time they spend in the website. And as you can see here, Okay, the bounce rate against the pages per visit. The lower the bounce rate, the bigger the number of pages per visit. Okay, and now we are performing the regression of this. We have so step number one. What is step number one? Once you have the data, step number one is to perform the graphs. To perform the graphs of the regressions we want to perform. Okay, scatter plots. So the explanatory variable would go on the x-axis, and the dependent variable would go on the y-axis. Okay, this explanatory variable will go on the x-axis, and the explained variable will go on the y-axis. Okay. Here we are, and we'll start by the regressions. By the regressions. This is the data set here. There's a problem here with the data set. You can see that we have 26 points, okay? And this is not enough. That is not enough. Because we need at least 30. So I'm moving to a different PowerPoint to explain these practicalities. Okay. I'm the second PowerPoint now. The two PowerPoints are already uploaded in the Google Drive. These are for the partners of the project. For those who are not partners, everything would be as it is a European Union project. Everything is published open source, open access. So everything will be published in the website, on the website, the PowerPoints and the recordings as well. The PowerPoints and the recordings, okay? So which is the problem here? Here, I'm showing a table of the data, and you see that we have 26. The size of the sample is 26. Okay, it's not. And some statisticians suggest that a minimal sample size of 30 observations are required in order to perform a regression. But the rule may not always be sufficient. Okay, the rule is that generally the larger the sample size, the better. The larger the sample size, the better. But if we have 30 observations, we could do something. Okay, with 30 observations, we can do something. So here we have extended the size of the sample size to 33, as you can see here. Can you see it?
Yes.
33. With 33, we can do something. Okay. So as we start performing the regressions. So first regression, we want to analyze which is the impact, causality between return rate and pages per visit, okay? So the dependent variable is pages per visit, and the explanatory variable is return rate, okay? Return rate is on the x-axis, so it is the explanatory variable, and the dependent variable, the variable we want to be explained, is on the y-axis. And this is the regression. We will perform all regressions in the second session with open source software. Okay, with open source software. So as we perform all the calculations with open source software. Okay, so first of all, which is the sample size here? PV is pages per visit, dependent variable. Then we have the sample size. We have 33 observations here, 33 observations, okay? Can you see it? So this is the minimum, let's say. The explanatory variable is return rate. And we start checking the checklist, okay? In order to have a reliable, let's say, regression, we start with a checklist. First of all, goodness of fit. Goodness of fit. What is the meaning of this? The meaning of this is whether this regression is a good regression. It is the fitness of the points with the line is good enough, okay? So we go to the R square here, R square. Can you see the R square here?
Mm-hmm.
And adjusted R square. And the R square is 0.48. So it seems that it's not 0.9, it's not 0.8. Maybe it seems that so-so, okay? So-so. But then we perform a F statistic for the R here. We test with an F statistic for the R here. And we see that the R is significative. So what we are saying is that this is a reliable fit. The goodness of fit is reliable, okay? Okay. I'm going to draw some examples. Oops, I'm sorry. My drawing is not very good, but okay, and Y, this is Y.
Mm-hmm.
This is the line, this line, this is the fitness, the points, okay? The observations. I don't know whether I managed to, I'm trying to draw, but so we have an R, this should be a line, okay? This is Y. Okay, again. As you can see, I'm fighting with the system. At 1 point, 2 points, 3 points, or less. This should be a line, okay? If we performed here a regression, this would have a high R, because all the observations are very close to the line, and a significative F test, okay? Because the goodness of fit is very good, okay? In this case, we have a lower R. This means that the points are a little bit scattered around the line. Can you see it?
Mm-hmm.
But the F test is significative. So this means that the goodness of fit of test is a good one. We can have a case like this, for instance, in which you have the regression line here, okay? And the points maybe would be far away from the line, maybe like this. Imagine, okay? Far away from the line, but you see very clearly that they are moving. There is a pattern. There's a clear pattern a linear pattern here, although they are far away from the line, there's a clear linear pattern here along the regression line, okay? In this case, R square would be very low, but the F statistics would be significative, okay? In this case, the R square would be low, the R square would be low, but when we perform the F test, it will be significative. The R square is low because the lines are not very close to the adjusted line, okay? But you can see that the line is a good summary of the trend of the points. Can you see it?
Yeah.
And so this is why the if statistic is significative, okay? So first of all, as I mentioned, we make sure that we have more than 30 observations. We draw the graph. X is the explanatory variable, Y is the displaying variable. We perform the regression and we start with the checklist. The first point would be to check goodness or fit, the R square and the F statistic, okay? Okay. Any question? Okay. The second thing would be to check for homokedasticity. What is the meaning of this? The meaning of this is the following, okay? Imagine that we have a data set like this. We have X and we have Y, okay? And then we have the points. Points, more or less, the points that have to, the observations, okay? Observations, okay? So the unbiased line would be this one. Can you see the unbiased line?
Yeah.
Yes. What happens with the outlier? Maybe I have an outlier here. Can you see the outlier here?
Yeah, alone.
Yes, alone. If you have an outlier and you test for heterodynamicity, the test will tell you that the observations are not distributed in an even way with the line, because all these points are distributed in an even way but you have one line which is not close to the line, okay? Which is the problem of this? The problem of this is that if you calculate the regression analysis of this by including this point, the regression would be something like this. This point is pushing up the line upwards. Can you see it?
Yes.
So this outlier is pushing the line upwards. And this means that when you perform this regression by including this outlier, the estimation is biased. The estimation is biased because you have an outlier which is generating a bias in your regression, okay? So we need to solve this. We need to solve this, okay? Because we know that the good regression is the red line, the red line.
The time for red wine.
But we have done the regression by including the outlier as well, and it is biased. It is biased. The regression is biased. Okay? So we need to solve this problem. Okay. How did we know that we have heterodynamicity? Because we performed the test here. Okay. We performed the test here. Okay. So we performed the test because we have to make sure that the test performed says that there is no problem at all in heterodynamicity, so as all the points, all the observations are very nicely located very close to the line, or at least close enough and nice enough along the line, okay? Okay. And so as there is no bias, so how can we correct this problem? The problem, we corrected this way. We generate a fictitious, a dummy variable. So a dummy variable would be here, which is the outlier. In this case, the outlier is scholar, okay? Can you see the outlier here? It is scholar. The word scholar. So we build up a variable which is 0
Mhm.
for every single point observation step for scholar. It is 1. Okay, for scholar it is 1, and we include the dummy variable within the regression here. Can you see the dummy variable here?
Mhm.
So this is the dummy variable, a fictitious variable, which is 0 step for scholar, and for scholar it is 1. Okay. Okay. Any question? And then once we include the dummy variable, we perform the regression again. We perform the regression again. And this is the correct regression, okay? In which the dependent variable is the pages per visit. The bigger the pages per visit in our website, the better, because we want visitors to come to our website and to stay. So the bigger the amount of pages per visit, the better. Okay, so the dependent variable is pages per visit. Then the explanatory variables. The explanatory variables, we have the constant. We always include the constant, no matter which model, the constant is always there. Okay, so this is a rule. We always include the constant. Then we have the explanatory variable, return rate. RR is return rate. Okay, and we have included the dummy variable for scholar because scholar is the outlier. This is the outlier, this one here. Can you see the outlier?
Mhm.
So this outlier, if you perform the regression with the outlier, it generates a biased regression line.
Mhm.
Can you see it?
Yeah.
So we need to correct for this with this fictitious variable, okay? So because we know that the unbiased estimate is this one, okay? That one, that is the unbiased one, okay? Okay, so again, we include the fictitious variable and we start checking again. Goodness of fit. The R square is 0.48, okay? And the F statistic, the probability of the p-value of F statistic is 0.0 here. This is the R square, okay? So R square is 0.48. It's not a very big R square because you see here that there are some points. The points are around the regression line, all the observations, but they are not so nicely positioned along the regression line. And this is why the R square is not so high. The R square should be something between 0 and 1. But then we perform this F statistic to see whether the R square is significative, and it says that it is significative. Because in order for the F statistic to be significative, the p-value has to be smaller than 0.05, okay? So this p-value is smaller than 5, okay? Oops, 0.05. Yeah. Here, the F statistic, it has to be smaller. The p-value, this value here, has to be smaller than 0.05, and it is smaller than 0.05, okay? So this means that it is significative, and it is the goodness of fit is correct. what happens with heterochalasticity? The F statistic, the white heterochalasticity test is telling us that having corrected for the outlier, there is no heterochalasticity. Okay, so what the test is saying us is that there is no problem of an outlier, because in this case, this value, the first decimal should be always bigger than 0. Okay, you see that I'm explaining it in a very practical way for non-statisticians trying to work out how to work in a proper way in real life. Okay, so here we see that we don't have a problem of heterochalasticity. So all the points are very nicely somehow around all the observations around the regression line. Okay. So first problem, homochalasticity, it is fulfilled. The next condition, absence of multicollinearity. Well, you don't have a problem of multicollinearity because this happens when you have more than one explanatory variables. When you have more than one, explanatory variables, maybe it could happen that explanatory variables are correlated among them, and when they are highly correlated, the estimate in OLS, because we are with OLS, the estimate, it could happen that the coefficients are biased, okay? So we don't have a problem of multicollinearity here because we only have one explanatory variable, which is return visit. Okay. And last condition to be checked here is the normality of residuals. The normality of residuals means the following. What is a residual? We have X and X. We have the observations, okay? Or less, imagine that the observations are like this. Excuse me. Have the observations more or less like this. Excuse me. Again, these are the observations, okay? The residuals are the real value, the real observation minus the estimate. The estimate is the line, okay? Estimate, the line. So it is this Y minus the estimate. It is this distance. These are the errors, because we are minimizing errors, okay? Minimizing errors. So we are minimizing errors. The best situation to minimize errors would be that the mean of errors is 0, okay? Because the smaller the errors, the better, okay? The smaller the errors, the better, okay? Okay. So what is the logic of this? The logic of this is that we have a normal distribution of errors, more or less. I'm sorry because you see that I'm not very good drawing, but we have, this is the Gaussian bell for errors, okay? So we want errors to be very close to 0. We want errors to be very close to 0, okay? And normally distributed around 0. It makes sense because we want errors to be 0, okay?
Yeah.
Or very close to 0. And this is why we perform the test for residuals. because this is the Hakavera test in which we are checking whether residuals are normally distributed, okay? We are checking whether residuals are normally distributed around 0, okay? And here, this is the histogram of residuals, as you can see. The histogram of residuals and the Hakavera. And the result is that it is, in this test, if the p-value is different than 0, then it follows a normal distribution, okay? Here the probability is 0.26, so this means that the first figure is bigger than 0, so this means that it does follow the distribution of errors or residuals does follow a normal distribution, okay? Any question? Okay. 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 So this is a good fit. This is a good fit. The only thing I would say that maybe it will be better with 50 observations or 100 observations or more, because 33 maybe it's not big enough. Okay, this is one thing. This in practical terms, this means that maybe we could improve by increasing the number of observations. Now let's go to the coefficient. What is the meaning of, well, first of all, it is significant, okay? In order for the coefficient to be significant, the p-value has to be smaller than 0.05, okay? Has to be smaller than 0.05, okay? 0.05. This one has to be smaller than 0.05, and it is smaller than 0.05. So the meaning is that this is the coefficient as significative. The constant is significative, the explanatory variable return rate is significative, and the fictitious variable or dummy is significative. The three of them, the p-value is smaller than 0.05, so the three of them are significative, okay? So somehow we can say that we are doing good job. Maybe they could be, we don't know, an omitted variable bias. Maybe there could be, we don't know, omitted variable bias, okay? But we will not go into this. So, last but not least, having seen that the goodness of fit is correct, that there is homokedasticity, that there is no multicollinearity because we only have one explanatory variable, and that there is normality of residuals, we check the coefficient and read the coefficient, okay? So the meaning of this is when the return rate increases, the recurrent rate is percentual increase, okay? It is percentual, it is this. The return rate is a percentage between 0 and 100. So when the return rate increases 1 unit, when the return rate increases one unit, the pages per visit increase 0.03. This is the meaning of this. Okay? When the return rate increases 1 unit, the number of pages per visit increases by 0.03. Okay? This is the meaning of this. Any question? So this is excellent news for any business. We do feel that it is interesting for institutional websites or even for companies' websites to get to know these figures, okay? how the website is performing in terms of analytics and also to perform inference. Okay, so now we move on to a second regression. Now we move on to a second regression. The second regression is the following. The dependent variable is the number of pages per visit, and the explanatory variable is bounce rate. Okay, this is the X explanatory variable, and this is the Y pages per visit. Okay. Would you say that this has a good R? What about R here? Yes. The first thing we do is we draw the scatter plot. No, we draw the scatter plot. This is the scatter plot. Okay, and we see that the observations are very nicely around the regression line.
Yeah.
So, and very close to the regression line.
Yeah.
So we don't have a graph like this in which they were around the regression line, but a little bit
Far.
in an uneven way or far. Okay. In this case, they are very close. The observations are very close to the line. So the R should be high. R should be high. Okay. The R squared should be high. Let's check it. We go and check it. This is the R squared. Okay. The R squared is high. It is 0.86. It is high. Okay. So this means that the observations are nicely around the regression line. And the F statistic is meaningful here. Okay. F statistic, which is the test for the R square, is meaningful. Okay. So what we are saying is that the goodness of fit is excellent. The goodness of fit is excellent. Okay, the goodness of fit is excellent. Okay. Next step. What happens with heterokedasticity? Well, you see here that we corrected. We included two dummies. Can you see the dummies? We included two dummies. We included two dummies to correct for outliers. Okay. To correct for outliers, because when we performed initially the white heterokedasticity test, in the test we saw that the p-value was something like this, for instance, or something like this. So the two first figures were 0. So this means that you have a problem, that all the points are not evenly distributed along the line. Okay. So as we saw, in order to correct for outliers, we include fictitious variables. So we build up two fictitious variables. Okay. Two dummies.
The dummies.
Yes, two dummies. One for this platform. This is a reference site. So we have one for the reference, for the reference site. Then we have here everything 0 except for the reference site. Okay. In another one for the keyword scholar. Another one for the keyword scholar. So we included two fictitious variables to correct for heterokedasticity. Okay. 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 And then we perform the regression analysis. The dependent variable is pages per visit, and the explanatory variables we have bounce rate, and then we have two fictitious variables. Okay. we include it. And then we check for heterokedasticity, and we see that it is homokedastic. We don't have any problem by including the dummy variables with the outliers. We don't have any problem at all. So they are homokedastic. Okay, and then we check the normality of residuals. And then, because we want residuals to be very close from zero, the aggregation of the squared residuals to be very close to zero. Okay, and we perform the Hackevera test. In this case, there are several tests for normality of residuals. I use Hackevera. So here you see the residuals. The test says that the residuals follow a normal distribution, and it is we prove the normality of residuals. Okay, we have proved normality of residuals. Okay, so this means that in the checklist here we have goodness of fit. They are homokedastic. We don't have multicollinearity because we only have one explanatory variable, and the residuals follow a normal distribution. Okay, and last but not least, we analyze the explanatory variables. Are they significant? And the answer is yes. The constant is significant. Bounce rate is significant, and the two fictitious or two dummy variables are significant. So all explanatory variables are significant, okay? Because all the p-values are smaller than 0.05. All the explanatory variables are smaller than 0.05. Okay. So having tested for all the diagnostics, we call them diagnostics, okay? We go and analyze the coefficients. And the coefficient is the following. When bounce rate increases by 1 unit, the number of pages per visit increase by minus, so we have as minus 0.09. Okay, 0.09. Okay, as you can see here, 0.09. And well, the good news is this negative, so it makes sense. We have a negative slope. The bigger the bounce rate, the smaller the number of pages per visit. Okay, and when bounce rate increases by 1 unit, the number of pages per visit decreases by 0.09. So if I am managing a website, the best thing to do is to diminish its bounce rate. If a web manager, if a culture web manager manages, excuse me, to repeat as I'm repeating the word, to diminish the bounce rate of the website, this would be excellent news, because by diminishing the bounce rate, you increase return rate, and you also increase the number of pages per visit, and also the duration of the visit. Okay, so by decreasing the bounce rate, the overall quality of traffic increases. Okay? By decreasing the bounce rate, the overall quality of traffic increases. Okay, any question? Okay. This is this coefficient is this one. Okay, this one. Okay, you see that this keyword scholar is performing above average. Okay? This means that this keyword is performing extremely well for us. This is the meaning of this, okay? This keyword, Scholar, is performing extremely well for us. And this observation is not along the regression line, as you can see. And this is why we have included it with a dummy variable, okay? The good thing is that we are able to quantify how well this observation, this variable Scholar is doing for us. We know that every time a user uses the keyword Scholar, the number of pages per visit increases by 2.25. 2.25. Okay, 2.25. That is very well, very well. Okay, so this means that this keyword is strategic for us. This keyword is strategic for us because this keyword is generating traffic of very high quality for us. Traffic that comes, stays, and visits a lot of pages. Okay. So if I were the manager of the website, I would take care of all traffic sources, but obviously I would take care of this keyword Scholar. Any question? Okay, so let's have a 10 minutes break. Let's have a 10 minutes break and we will continue within 10 minutes.
Okay.
With a new regression with cross-sectional data. Thank you so much. Bye-bye.
Thank you. Bye bye.
Thank you.